Welcome everybody to our video today on mathematical growth models. This is really going to be kind of like an introduction to starting to look at exponential functions. You will need a calculator for this lesson today, so if you don't have one out right now, pause it and get ready to go. And we will get started right now. So first, we're just going to look at some growing patterns, okay, and then we're going to talk about what kind of growth each would be. All right, so the first one, 4, 7, 10, 13. What is the pattern? Well, what we're obviously doing is we're just adding 3 to the previous term, right? So adding 3 each time. The next term would then be 16. This is called linear growth, okay? In our last unit, we talked about it being an arithmetic sequence, but it's just called linear growth. The second one, 4, 9, 16, 25. These are the perfect squares. So next term will be 6 squared, which is 36. What kind of growth is this? Well, that's all just quadratic because it's squares. So this is a quadratic growth. The last one, 1, 2, 4, 8. So the pattern would be that we're multiplying by 2 each time. Next term would then be 16. What kind of growth is this? So in our sequences and series unit, we called this geometric sequence. But really, this is called an exponential growth. It's called an exponential function. Okay? So here we have 3 different types of functions. The red one is linear, the green one. So let's start with the red function. This is linear, all right? So if we're just going to put -3 in, -2, -1, 0, 1, 2, 3. And if we plot those points, so -3, -6. And then we're just basically going up by 2 each time here. And I'm close enough. Close enough to that graph. All right, so it should look something like that. Okay, and then the green one is quadratic, so -3 squared. -2 squared, -1 squared, 0, 1, 2, and 3. So plot those points. Our graph should look something like this. All right, and then our blue one, our exponential, so 2 to the -3 is the same thing as 1 over 2 cubed, so 1/8. Then 1/4, and then 1/2, 1, 2 to the 0 is 1, 2 squared, 2 to the first, 2 squared, and 2 to the third. Look like that. So we're plotting those points here. So 3, 8, 2, 4, 1, 2, 0, 1, and then we're just starting to get flattening out here. It should look something like this. Okay, so we have a linear in red, a quadratic in green, and an exponential in blue. All right, so let's talk about this next one here. Levi has been offered a job with 2 salary options. Option 1, he gets $50 grand in his first year and a $2,500 raise each year. It's pretty good. Option 2 starts at $3,000, which is terrible, but it triples every year. Well, let's see how that comes into play here. So the first one, this is linear, okay? So we know this as, we called it in our sequence and series unit, we called it an arithmetic sequence. So it's basically just start at 50,000, add 2,500 t for every year of t. The second function, we called this, well, it's exponential, but we called it geometric in our last unit. It starts at 3,000, but then it triples every year. So after 3 years, which option pays more? So I'm going to call this S1 of t and S2 of t. S1 of 3, we just put 3 into here we would get 57,500. S2 of 3, if we put 3 in here, be 3,000 times 3 to the second power, so 3,000 times 9. And he's already at 27,000. So in the fourth year then, so it says after 3 years, so the fourth year, add another 2,500 to that. Option 1 would be 60,000, but triple another one, and it's going to be 81,000. So the first option is only the better option for 3 years, and after that, the second option is the much better option. Why is that? Exponential growth grows a lot faster than linear growth. And that's what we're seeing happen in this problem. So here we have the exponential growth or decay formula, okay, where A of t is your amount at time t. A sub 0 is your initial amount or your starting amount. R is your rate of growth or decay. If it's positive, it's growth. If it's negative, it's decay. And T is your time. It's usually in years, but not always. It could be months or days or minutes or seconds or anything like that. You just got to read the problem. All right, so our first example with this, suppose in a controlled environment, a certain bacteria culture grows at a rate of 2.4% per day. There are initially 1,000 bacteria in the culture at time 0. Write a mathematical model describing the amount of bacteria after t days. All right, so we're going to use this right here. A sub 0, 1 plus or minus r to the t. A sub 0 is 1,000. That's how much we start with. 1, it is growing, so it's plus. And we don't want to put 2.4. We want to put 0.024. I'm going to change that to a decimal to the t. All right, we're going to graph this equation in our calculators. So go ahead in your y1 here, 1,000 times 1 plus 0.024 to the x power. All right, you're going to have to probably change your window up a little bit here. I gave you a little hint there on the graph. Negative 90 to 90, and then you can go a little bit below 0 to 5,000. We know at 0 we should be at 1,000. Okay, but otherwise the graph should just look like this, growing pretty quickly. So how long will it take the population to double as in get to 2,000? All right, so we're going to want to see if the 2,000 line is right about there. We want to know when that graph would hit that. So we've done this, some of this before. You're going to go to y2 and put in 2,000 and go back to your graph and find the intersection point. So second trace, intersection point, and then just scroll over until you're on top of that intersection point. And you should be getting 29.226 days. How long will it take the population to double again? So just go back to y1 and change 2,000 to 4,000. And go back to your graph again, and we will find the new intersection point the same way we found the intersection point on the last one. Second trace, number 5 is intersect. Scroll over until we get on top of that intersection point. And I'm getting 58.453 days, which means this minus this will get us our answer. It takes 29.22, or no, let's do that math. Let's do that. 58.423 minus 29.226, 29.197. So it's pretty much the same number. It's really close. Days. So what we're doing here is we're subtracting this. 58 minus 29 there to get that answer. All right, so how long will it take the population to double again? So we're going to have to change our window this time. We have to go up to at least 8,000. So I'm going to go to 9,000. And you probably have to extend the X max as well. Let's go to maybe 150. And if we graph that, along with Y2, change that to 8,000. And one more time, second trace, intersect. Scroll all the way over until you get on top of that intersection point. And I'm getting, this is going to be the 87.679 days. So how long did it take to double again? We're going to do this minus that number. So 87.679 minus 58.423. And we're getting basically the same answer, 29.256 days. So essentially, it's taking a little more than 29 days to double every single time. Technically, we're supposed to get the same answer every time. The calculator is not perfect. It's doing the best it can. But the point we're trying to make here is that it takes the same amount of time to double. Okay, so how to get from 1,000 to 2,000? 29 days. 2 to 4,000? 29 days. 4 to 8,000? 29 days. If I want to get to 16,000, another 29 days. Okay, that's what we're talking about in F. In G, how would your results in an equation be affected if the initial population was 500? It wouldn't really affect anything much. All we would do is just change this to a 500. Okay, and besides that, everything would pretty much be the same. Okay, it would be, the graph would look similar, just be a little bit lower, closer to the x-axis to start. Okay, it'll still grow at the same rate though. Okay, last one here. Suppose a certain radioactive isotope decays at a rate of 3 over 128 per day. So that means that 3 over 128 of the isotope that exists at the start of the day decays into another form. Initially, 1,000 milligrams isotope exists. How much exists at the end of the first day, second day, the third day? All right, so we're actually going to skip that right now, and we're going to go to B, write the mathematical model. So that's going to be 1,001 minus 3 over 128 to the t. All right, that's something we can go ahead and throw into our calculator here. 1 minus 3 over 128 to the t. All right, and then I'm just going to go ahead and put 1, 2, and 3 into that equation. Now, we have a couple different ways we can do that. But if you want to just go to your table, and you can see those numbers pretty easily there. So on the first day, there'll still be 976.56 milligrams. On the second day, 953.67 milligrams. And on the third day, 931.32 milligrams. Question C says, graph the mathematical model from bacteria problem above and model you wrote in the previous bacteria problem. Set your domain here to negative 100 to 100. So let's do that. Negative 100 to 100. And range 0 to 2,000. All right, we got to go back into y equals and put this and this into y1 and y2. And what you should be seeing here on the graph, so this is the bacteria problem, and this one is the isotope problem. What you should be seeing here is the graphs look very, very similar. The bacteria problem goes through 0, 1,000. I'm going to move that down a little bit. But it's going up pretty rapidly. The isotope problem, it also goes through 0, 1,000, but it's going down very rapidly. So this is growth, this is decay. All right, growth is going to be going up rapidly. Decay is going to be going down rapidly until it gets closer and closer to 0. Okay, so the last number here, write a sentence or two to describe the relationships between the graphs. How are the base numbers 125 over 128 and 1.024 related? All right, so this is what we get when we subtract here. And this is what we get when we added here. So that basically what we're doing is that's what we're multiplying by every day. If we turn this into a geometric sequence, those numbers would be our ratios. Okay, that's it for today's lesson. Thanks as always for tuning in, and we'll see you again next time.